Okay, the next topic is the Mohr'sCircles. So this topic is kind of like paving our way to the topic of soil strength, which is means to be the most difficult part uh, of concept when we talk about soil behavior. How strong is the soil, and you directly related to your engineering design, your foundation design. So first of all, I'll talk about the geotech conventions. Our geotech world is upside down than the structural, because structural, you care about compressions, and structural, you care about tensions, right? Because think about concrete. Concrete is much weaker in tensions than compressions. So if you can take care of the tensions, pretty much you can take care of the compressions. But in our geotech world, it's the other way around. It's because it's like the majority of loading we handle is in compressions. So that's why for normal stress, let me use red. I think red would be more clear. For normal stress, compressions is positive. Normal stress, we use sigma. So sigma means normal stress in geotechnical engineering. And in tensions, it is negative. Or maybe I better spell it out. So this is negative. So this is negative sigma in tensions. And in shear stress, oops. Oh, my pen is not working very well. What happened? So in shear stress, oh, the short terms is a tau. So the Greek letter tau is shear stress, and we represented the positive sign is anti-clockwise. So anti-clockwise is positive. So this is anti-clockwise. And in clockwise is negative. So negative is anti-clockwise. And for the solid elements, you must have both positive and negative shear stress, which means the balance out. You need to balance out for equilibrium. So those are sign conventions for geotechnical engineering. There's a couple more terminology right there. First of all is principal stresses. So principal stresses means the normal stresses on plane where shear stress is 0. So very important. You need to understand what does it mean by principal stress. So you have sigma 1 and sigma 3 there. we're talking about what is sigma 1 and sigma 3. But like we assume there's no shear stress. So those are the shear stress. Remember shear stress, we say tau is equal to 0. So there's no shear stress. So the principal stress are the normal stresses on the plane. So when we say about plane, oops, that's not a good color. So when we talk about the plane right here, this is the plane. So those are the plane. And on those plane, there's no shear stress, which is the tau equals 0. And the principal plane is the plane that we just highlight, plane on which the principal stress adding on. And give us the sigma 1 and sigma 3. And sigma 1 is the maximum principal stress. And sigma 3 is the minimum principal stress. So we know what are principal stress. The stresses adding on the plane that doesn't have a shear stress. And there could be many different like principal stresses. But we look at the maximum one and we look at the minimum one. Those are our sigma 1 and sigma 3. Those are our sigma 1 and sigma 3. And sigma x and sigma y are the stresses on plane that the shear stress are not zero. So imagine this is your soil samples. Imagine this is your soil sample. Or imagine you are doing, like, remember your concrete lab. So you have done your you have taken material class, the civil engineering material class. Remember you crash concrete samples, right? When you have like trying to like cracking this or compressing this soil sample or this concrete samples, there's many planes on this sample. So those are the principal plane. So those are the plane that doesn't have a shear stress, top and bottoms, and also have the sign. There's no shear stress. But within like within this like a principal, I mean like this concrete samples, you have many different planes, infinitive like a plane on those on those concrete samples. And those planes, you will have sigma x and sigma y. So those are the stresses on the plane. Throughout this lecture, you need to understand what is sigma 1 and sigma 3. And what does it mean also by sigma x and sigma y. So those are the terminology you need to be very comfortable on. And also what is like a sigma alpha and tau alpha. So sigma alpha and tau alpha, those are the normal stress and also the shear stress on the shear plane. On the shear plane with an orientations of alpha. So if this is your, for example, if this is your concrete samples, our case soil samples, if you're loading it, if you're applying compressive force to load on it until it fell, oops. So this is the failure plane. So on this plane, it has an orientations of alpha. And also it has a stress adding on it, the normal stress, and the shear stress with the orientations alpha adding on the plane. Any questions? And also like there's isotropic stress is the case that sigma 1 equals to sigma 3, which is the vertical stress equals to horizontal stress. And also there's one terminology, sigma D, which is the deviated stress. Oops. Deviated stress, which is equals to sigma 1 minus sigma 3. So sigma 1 in geotech is the vertical directions, and sigma 3 is the horizontal directions. So you have been calculating the vertical directions. And I think back to lecture 3, we also talked about how to calculate the horizontal directions, horizontal stress here. For you to understand the difference between sigma 1 and sigma 3 versus sigma x and sigma y. So we get back to there. And always get back to this point. But like the most important difference is sigma 1 and sigma 3 add on the plane that you don't have a shear stress. You don't have a shear stress. And sigma 1 and sigma 3 are the maximum and minimum stresses where you don't have a shear stress. So we understand all this like element stresses. And then like we can represent the whole thing with a circle. So that's what like a Mohr has done like many years, I think like a couple hundred years ago. So he can claim the credit for he's a mathematician, so he can claim the credit to call this to be a Mohr'sCircles. So when we have solid elements one more times, we have the sigma 1 and sigma 3. So those sigma 1s are the maximum principal stress adding on the principal plane. So this is your principal plane, right? Because you don't have any shear stress. You only have a normal stress adding on it. But just like you're loading your concrete samples on the plane that you are loading on it, you don't have the shear stress. But the shear stress developed within within your the center of this, or like the center part of the samples. But like when you're loading on it, you just apply a normal force. And in the ground that we're working on, we also have the horizontal like a pressure, right, adjacent to your solid element, the K0 that you have been calculating. So that is the sigma 3, the horizontal stress. So you have sigma 1 and sigma 3 adding on it when you cause the failure. You also have on any plane within your elements, you have the normal stress and also the shear stress with an angle orientations of alpha, and orientations of angle alpha. And if we just look at this, focus on this like this plane right there. So what we're doing now is we just focus on this plane, the failure plane, on this failure plane. So this is the failure plane. We only have the failure plane. And we can, again, this is our sigma 3 and this is our sigma 1. And we have the normal stress and shear stress adding on this plane with the angle alpha. And we can further like define the dimensions of each length right here. So we define this length to be dy, and this length right here to be dx, right there. And this length here, it's hard to draw, but like this length here to be d sub s, ds. So we know the stress and we know the area. So we have the length times the dimensions into the page, which can be a unit, can be 1. So we know the area and we know the stress. We can calculate the force because like the stress times the area equals to the force. And just like a static cost. So now we summarize the static equilibrium calculations. We summarize the force in the horizontal directions and also the vertical directions. So this is the horizontal directions, and this is the vertical directions. So we summarize all the forces. So for example, the horizontal direction, right? So the horizontal directions, the force will be equals to sigma 3 times the area, which is dy. So dy times 1 give you the area. So the force, the stress times the area give you the force, and then equals to the horizontal component from this force, sigma alpha, and also the horizontal component from the tau alpha. You take care of the angle with the sine alpha and cosine alpha, and then times the corresponding area. So you try to look at the horizontal directions. You summarize the force right there, and then also do the same thing for the vertical directions. Vertical directions. Now you have sigma 1 instead of sigma 3. You also take care of the components from the sigma alpha and tau alpha. So you have those two equations, and then you work through the equilibrium, and also like a trigonometry. You from the triangle that you have, you take care of the dx and dy, and both of them now is in terms of ds and the cosine alpha on sine alpha. So you have those 3 equations, and if you work on those 3 equations, so those are just math. So working through all this math, so I provide you the solutions already. So I highly recommend you get a blank sheet of paper after this lecture, and then see whether you can devise all this formula. And at the end of the day, what we want to achieve is this formula. This formula is represented by equations of circle. Because the whole concept here is try to transform element stress to a circle. It's done by Mohr, so that's why they call Mohr circles. We have, at the end of the day, we have this like a circle equation of circles, and it help us to solve a lot of like a geotechnical problem in this mathematical formations. Why we need to do this? So this kind of transformations. Why we need to do this? Because after we express the whole thing as a circle format, it give us very powerful, very useful tools to solve for the mathematical interests that we have. So let's look at these equations. So when you see these equations, you need to understand this is from the solving the static problems out of equilibriums from given like a solid elements. So after we have like these equations, we can compare with the equations of the so this is the equations of circles. So I hope everyone we call it algebra. And what the information is given you here is this is the radius, right? So this is the radius. And these 2 points are the center, right? Which means this point is your center. So you have x coordinate of x0, and the y coordinate here is 0. So the center is x0, oops. And 0. And the radius is r. And we organize we have reorganized our equations to a circle format, which means now this is my y-axis and this is my x-axis. And this is the small circles. So whenever we say Mohr'sCircles, which means we are at a space of normal stress as the x-axis and the shear stress as the y-axis. So again, terminology. So we use to express the shear stress as tau, right, for geotech, and the normal stress as sigma. So normal stress again means like, you know, adding perpendicular to the plane, and the shear stress means you're parallel with a plane that you're looking at. And those sigma and taus come back to us on the Mohr'sCircles. So pretty much if you compare it, like, you know, your y is right here and your x is right there. So this is your x and this is your y right there. And then like your center, we're speaking of the center. So this is my, oops, x naught. Oops. This is my x naught. And my y naught is here, which means the center now is at a coordinates of 1/2 sigma 1 and sigma 3. So this is my x naught, and the y naught is 0. And don't forget about this. This is your radius. So my radius is, I don't know what happens. So the radius is 1/2 of sigma 1 plus sigma 3. So which means this point is your center. And the radius here is 1/2 sigma 1 plus sigma 3. And this point here is my x naught, y naught again. When you're loading on this soil elements, all the stress state that happens like inside your specimens, it just can be represented by these Mohr'sCircles. Because everything, remember, everything we develop it, start from basic, start from the static, and like a very general genetic representations, just all the forces, all the principles, and maximum and minimum principal stresses, sigma 1, sigma 3, and also the stresses on any shear plane, angle alpha. So now, these circles can represent the whole thing. And remember, we talk about sigma 1 and sigma 3. We talk about sigma 1 and sigma 3. If we talk about like at this point right here, mathematical wise, can you guys envision like what should this point be? Should this point be sigma 1 or sigma 3 or sigma alpha? So what is, again, the definitions of sigma 1 is the maximum principal stress. And what is principal stress? Principal stress means they add on the plane that you don't have any shear stress. So now we are at the plane or the locations that you do not have any shear stress because the y-axis is equal to 0. So that's why, and this is the maximum along the sigma axis, because now all the stress is represented by the circles, and this is the maximum point on the x-axis. So that got to be a sigma 1. So now this point here is sigma 1, and likewise this point here and sigma 3. and sigma alpha. So the equation of the sigma alpha is any points on the circles. So sigma alpha is more than one value. It depends on the angle. So sigma alpha means the stress on the shear plane, right? So sigma alpha means the stresses on any shear plane. So if you have a different like a shear plane angle, then you have a different sigma alpha. So sigma alpha means like any points on this circle with the orientations of known alpha. So any questions here? So that is the equations of the concept of Mohr'sCircles. Start from a free body diagram of solid elements, and you work your way, becomes an equation of circles. Then you can represent all the different stress on a circle with a circle formula. Okay, so some like very quick examples. So one being powerful tools now with the Mohr'sCircle is we can find out the principal stresses and the maximum shear stress from the stress on perpendicular planes. So, for example, now you have solid elements in the ground, or like you imagine like a piece of solid element. You test it in the lab. You apply sigma x and sigma y on these solid elements, and also you apply a shear stress right there, tau yx and tau xy on this piece of elements. So in reality, you got all the reaction force. So now you apply all those stresses on the solid elements. So you can do this in the lab, and also you can do it in the field. So examples in the field, we are loading on the ground because of the structure. So this structure create a loading to the solid elements, and also like you have the canal consolidation, so you have the horizontal stress, and also like with a sloping ground, you may also like give you the shear stress. So you have all these stresses like in the ground, and you want to find out the maximum and minimum principal stresses. So the way you do it is like first you could based on the combinations of the stress, because remember the Mohr'sCircles is you have a stress of the normal stress and also the stress of the shear stress. So they give you a pair of coordinates. So first, maybe we look at this pair of coordinates. Okay, based on this giving like loading combinations, should sigma y, so I just talk about sigma y, should sigma y be a positive or negative? Positive, very good, right? And how about the shear stress now? The shear stress of like a tau yx. So should tau yx be positive or negative? Negative, right? Because this is a clockwise, very good. So we have a positive normal stress and a negative shear stress. So we have somewhere here. You could be a real number. So when you're like are actually doing in the lab or in the field, then like you have the exact number. But now like we try to generalize like the whole like a scenario. So you have the coordinate pair of sigma y and negative. Well, this is negative already, tau yx. Okay, we do the similar thing for the other coordinate pair. So you are on the same plane, so that's why they come with a pair. So the same thing, should sigma x be positive or negative? Positive, very good. But how about the shear stress tau xy? How about tau xy? Should that be positive or negative? It should be a positive, right? Because it's anti-clockwise. So I don't want to lose anyone. So if you lose like at this point, make sure you truly understand what's going on. Because like the positive and negative are being important. If you mess up on here, then the whole thing will, will be wrong from the very first step. So this coordinate pair, you have positive x, sigma x, and also positive like a positive normal stress and positive shear stress. So with that, we can form the diameters. And this will be the center. And you know the radius. So if you know like if you know the rate the center, oops. So if you know the center, and also if you know the center, and you know the radius, then you can form the circle. Then you can form a circle. So in exams or when you do like engineering work, so you need the compass, right? I always mix up the compass and protractor. So this should be a compass, right? So you have a compass, then you can draw a circle on the graph paper. So now you have this more circles. So now we can form the more circles. Because the concept is all the stress points. So all the stress combinations we talk about here, sigma y and sigma x, and also the tau yx and tau xy, they need to go through the more circles. They are like any points on the circles. So which means now you have 2 points. You have 2 points, and you can form these circles. And don't forget about our purpose here. Our purpose here is to find the principal stress. So we want to find out the principal stresses, which means we try to find sigma 1 and sigma 3, and try to find the maximum shear stress. That is the goal right there on the given stresses. So that's why I emphasize at the beginning, you need to be very good at. You need to be exactly know what you're doing, what is sigma 1 and sigma 3, and what is sigma x and sigma y. So in this case, pretty much they are giving you the sigma x and sigma y and ask you to find sigma 1 and sigma 3. So the sigma y and sigma x are given. And now, and also the shear stress. So you are given those informations, and you need to find sigma 1 and sigma 3 and the maximum shear stress. So now you have draw the more circles. So sigma 1 and sigma 3 is very obvious. So this point here is sigma 1, and this point here is sigma 3, and this point here is your maximum shear stress. So this is what I call the graphical method. That's what all the graphical method. And since you have these equations, remember we work on these equations together. Since you have this like equations, so you can solve for the whole thing analytically. So if you remember, like I formed these equations, it is in terms of both sigma 1 and sigma 3, and also the stresses of sigma and also the tau. So you need to be very, very like clear on here now. So sigma x and sigma y, it can be sigma alpha, right? Because sigma alpha pretty much is trying to capture everything. sigma alpha, like, meaning is like, the stress at any like given like plane orientations. So it can be like sigma x and sigma y. So if you solve for the whole thing, you again like if you are given the sigma x and the shear stress and also the normal stress, you can solve for the equations and then like solve for sigma 1 and sigma 3, and this will be your analytical solutions. Which means if you plug in, so if you are given like all the stresses here, if you're given all the stresses here, if you plug in these equations back to the stresses right there, you can solve for the sigma 1 and sigma 3 and the tau max that you need be same as the graphical solutions. So those are the same. But there's two ways to do it. Either like the graphical way or the analytical solutions. But I highly encourage, if you want to learn this, pretty much you need to know how to do it like as a graphical solutions, which means you understand. You learn all this is not try to learn just how to plug in the formula. A computer can do much better than you do nowadays, plugging in the formula. But like, your jobs and engineers is you need to communicate and express all the ideas to like the clients who may not have an engineering background, or like to your peers who could be a geotech or structural engineers. And then through your presentations, and at times you need to graphically illustrate the concept. So that's why we are training you to do the graphical method. This one, the analytical, you may want to check the answer, that's fine. But it's about like already understand children's and the concept of Mohr-circles. So any questions on here? So again, don't forget, this is your sigma 1 and this is your sigma 3. And this is your tau max. And any points right there on the circles, those will be your sigma and tau. So now, instead of like sigma x, sigma y, I give you a real number. So now sigma x is 190, like sigma y is 250, and also the corresponding shear stresses. We try to solve for sigma 1 and sigma 3. Again, be very comfortable on this terminology. So when they ask the principal stresses, means sigma 1 and sigma 3. Maximum shear stress is the tau max. And what stress are you giving? You're giving those sigma x and sigma y. So if you do it graphically, first you construct your Mohr space. So what is on the x-axis is the normal stress, and your what on the y-axis is the shear stress. So you have normal and shear stress, and you look at all your solid elements. That should give you 2 points. So your first point is here, right? If you look at this point, let me try to screen here. So if you look at your first data points, you have sigma x of 190, and that is in compressions, so it should be positive. And you have a shear stress tau xy in anti-clockwise, so that is like a positive too. So we want to mark down those stresses. So let's say this is like a 20, 40, 60, 80, 100. This is like a 200. So this is 190. And then positive 60. So we are at this point. So this is 190 and 60. So similarly, we do this coordinate pair. So we have positive 250, and now the shear stress is clockwise, so it's negative. So this is like a 200, 220, 240, and 260. So 250 is here, and then I have my second data point shear stress, which is negative 60. So which is here. So this is negative 60. This is positive 60. So with this, I have two data. I have 2 points, and I can form the diameters of the circles. And with this, I can draw circles right there. And now, just very straightforward. Then you can solve for my sigma 1. So this is 246.8 maybe equals 262 kilopascal. And my sigma 3 is about 140. And then like the maximum shear stress right there. Maybe about 70 kilopascal. So if you do it on a graph paper and with a complex, you would do you can do more accuracy than I do. So any questions? This is like the first step. So it's supposed to be like very straightforward. But when you add on, go on, keep moving on this topic, you know, it can be getting more and more complicated. So you solve this like graphically, and then if you plug in all this number back into those equations, you should get like a similar results. And I'll let you guys do the math yourself. Just plug in the equations. Okay. Next questions. Now here is find the principal like stresses and like a maximum shear stress with the following given stresses again. So this is also very similar. Like this example here, even though you're tilted with an angle, at the end of the day, you know, very similar procedure. Let me try to finish this like very quick for you. So again, the first step, go ahead, put down your sigma x and sigma y. And this is x is the sigma terms, and here's the shear stress terms. Your first coordinate pair is 8 and negative 2. Negative 2 is right here. And your next coordinate pair is here, 4 and 2. So you have the 2 points, and then you can form shear stress. You can form the Mohr-circles, black color. So pretty much then, this is your sigma 1, and this is your sigma 3, and this is your tau max. All right. So this should be simple enough like as examples. So next, we move on to the next method. Or before that, why we try to step up, because what we're able to do from now at this point is very limited, because we're only able to do given the sigma x and sigma y, and find sigma 1 and sigma 3. But that is not like the typical work or the very likely practice, or the very likely, like, what this type of problems will do. Because very likely you will know sigma 1 is, we should do, very likely we should do this the other way along. Because like very likely sigma 1 and sigma 3, just think about your concrete tests in your material costs. Sigma 1 and sigma 3 because that's the stress that you apply, but you don't know the failure stress that it happens. Usually that's what we need to find out, which means like, the typical problem should be the other way around. Sigma 1 and sigma 3, but you need to find the sigma alpha and tau alpha. And it can be like quite complicated. Like it will be much complicated than like, you have seen on the previous two examples. And like, in order to get there, we need more like tools. And one tool is one very good method that to help us to solve problem like that is what we call the pole method. So what is a pole method? So the pole method is help us to find stresses on any plane with given stresses. So we are not just limited on like, knowing sigma x and sigma 1, finding sigma 1 and sigma 3. With this pole method, we can find all the stresses. Could be like knowing sigma 1 and sigma 3, and then finding sigma x and sigma y, or the other way around. So this pole method is very powerful. But first of all, we need to know what is a pole. So a pole pretty much is a point, a very unique point on the Mohr-Circle is that all the plane need to cut through it. So when we're loading on our specimens, it will create an infinity plane inside the specimens, and which means like the planes are on the circles. And all the planes, at the end of the day, will point to one point, and that is the pole. And that is the pole. And for the pole method, if I use very simple language to try to explain it, is the pole method allow us to take advantage of the following. First, this pole method means one informations on the Mohr-Circles. So on the Mohr-Circles, we should able to identify the pole, and I will talk about how to identify the pole. The second, the Mohr-Circles should like come with the informations of stresses, which means sigma and alpha at any angle. And third is the orientations, which is the angle alpha. So that's like three informations right there for given Mohr-Circles, or given like on any plane or any loading, which means that when you're loading on a piece of soil elements or like concrete elements, when you're loading on like a piece of elements, you should have three informations on the Mohr-Circles: the pole, the stresses, and also the orientations of the plane. Because when you load on it, you can represent like the loading at any planes. And the planes, you have the stresses, and also you have the orientations, which is the angle alpha. And the hidden information is the pole. And the pole method means, so pole method means you can find out the third the third piece of information. Oops, my pen is not doing well today. Third piece of information. If you know any other two. So this is powerful, is because like this poll method allows you to find out the missing informations, building on the two that you already know. So for example, if you know the pole and if you know the orientations of the loading plane, then you can find out the stresses on the plane. Or like, if you know the orientations and you also, you know the pole, sorry, you know the orientations, you know the stresses, then you can identify the pole. So that's why the pole is very critical in the pole method. The pole is only like, a one point. Once you find it out, you know it. So after you know the pole, which means either you know the stress, then you can find out the orientations, or you know the orientations, then you can find out the stress. So that's why identifying the locations of the pole become very important in the pole method. Because once you identify the pole with the pole method, pretty much you can find out the orientations or the stresses, knowing like, the other one. So that's why, so that just pretty much is the pole method. So that is the pole method. So this is the most abstract part. So if you understand the pole method, pretty much like, it helps you to know that like to solve for this like Mohr-Circle's topic. And I guarantee you, your final exams, you will have a pole, you will have like a Mohr-Circle's problem, just like homework 8. So that's why like for exams, you need to have your compacts, and also your protractor. Make sure you have your protractors, and also you have your compacts ready. Or you can do something like me on the computer, but like you may feel more comfortable to use to solve the problem or graph paper. So for example, here you have this like elements. We have these elements here. So if I just look at, oops. If I just look at this piece of information, so or this piece of like a stress. Remember the pole method, right? Pole, stress, and orientations. So if I look at this stress, this like this, well, when I circle this, I better do this. So I also circle the plane. So this is the plane that I talk about. So if you look at this piece of information, we know the stress. So the stress is sigma x and tau xy. So sigma x is positive, and tau xy is also positive, right? Because it's anti-clockwise. So pretty much it's any point right here. So this is sigma x and tau xy, right? So we know the stress. We know the stress point. We know the stresses, and also we know the orientations of the plane. Because the plane is the orange line, right? This is the plane. So we know the orientations of the plane. So through the pole method, it telling us again, knowing the two, you can find out the third. So we know the stress, we also know the orientations, then we can find out the pole. So the pole is the point that also add on the plane, right? So the other locations, the other point that you cutting on the Mohr circles, this is the pole. Any questions? And we can double check ourselves. So now, if we look at this coordinate pairs, right? So we have positive sigma y and a negative tau yx. So we are right there. And the plane is this plane with this orientations. So we pole method one more time. Knowing the two, you can find out the third. And now we know the stress and we know all the orientations. We can find out the pole. And pole is the unique point. You only have one pole point on the Mohr circles on the given like a loading status of the stress elements. So this is the pole again. So here is like, pretty much just repeating what I'm saying. So the advantage of the pole method is, if you know like there are three items, you can if you know like two of the three items, you can find out the third one. So the three items, one more time, is the pole, the stress points, which is the sigma and the shear stress. And also, we know the orientations. So there's also analytical like maybe I don't want to like lose my momentum. Let me do an examples and I will get back to the analytical like but let's try to finish carry the momentums and try on examples. So now this questions is a little bit different than the previous two. Now you know the principal stresses because you know sigma 1 and sigma 3. But now you try to find out. So now you try to find out the tau and alpha, sigma alpha and tau alpha. So alpha equals 35 degree. 35 degree. So we want to find out the stresses on a plane that is 35 degree to your elements. What are the stresses? Given that you know the principal stresses, sigma 1 and sigma 3. So to do this, first let we construct the Mohr circles, the Mohr space. So we know sigma 1 and sigma 3. So sigma 1. So first of all, this is sigma 1. So this is like a 52 right there. So this is sigma and this is shear stress. And then sigma 3 is 12. So 12 is right here. Or maybe let me change the scale. So this is 10, this is 12. Let's say this is 12. And 10, 20, this is 20, 30, 40, 50. So this is 52. So I have my sigma 1 and sigma 3 right there. So with the diameters, then I can construct my circle. So this is my Mohr circles. Like this. So this is my Mohr circles. And now, remember the pole method. Poles means knowing the so the pole method. you have three items: the pole, the stress, and the orientations. So the questions is asking for the stress, and it gives you the orientations, 35 degree. So what we need to do now is find the pole, because if we can find the pole, then we will know about the stress. Because know the pole, we know the orientations. Knowing the two, we can find out the third, which is the stress. Okay, how do you find a pole? First of all, we can look at this plane right here. Oops. We can look at this plane here. So we know the stress, which is this point, and we know the orientations, which is this plane. So we only cut it through there. So remember, the pole means, right? So this is the plane, and this is the plane. Remember, the pole means like that the point that cut on the Mohr'sCircles, and every a plane need to go through that points, and you're only touching your Mohr'sCircles by one point. So this is the pole. And we can double check ourselves. So if we look at the other given plane right there, so this one right there. So we know the stress point and we know the plane. So this is the plane. And this needs to parallel with this plane, right? We know the point, which is 52 kilopascal, and need to says the same orientations on the plane that you're on the soil elements. So this is the plane. So you know the cutting point here is the pole. So that's the pole. So now we know the pole here. You know the pole, you know the orientations, you can find out the stress. So now we know the pole, and we know the orientations. The orientations is 35 degrees. So from our pole, if we draw like a 35 degree on our pole, the intersection point here is the answer that we're looking for. So this is like the answer that we need. So this is 35 degree. So here, 10, 20, 30, right? Am I correct? No, this is 10, 20, 30, maybe something like 38 right here. And here is like oops, sorry. So the scale needs, x-axis and the y-axis need to be the same. So this is 10, this is 20, so maybe about 18. So those will be our answer. How to find out the stress at a plane of 35 degree, and this plane must cut through the pole. So let's pick up the analytical solutions for finding those stresses on any plane that has a shear stress. So when you are given, for example, when you are given sigma 1 and sigma 3 in this case, when you are given sigma 1 and sigma 3 case, and again, at the end of the day, all these deviations right there should go back to our very beginning, that we set up our soil elements. So everything starts from a piece of soil elements, and this is like become a static problems. If you solve for the equilibriums, both vertical and horizontal directions, then from the free body diagram, you will obtain or you organize the formulas, then you obtain the equations of Mohr'sCircles, which is a circle format. So if you solve for this, pretty much like, like the case that you have sigma 1 and sigma 3, you try to find sigma alpha and tau alpha right there. So sigma alpha and tau alpha pretty much is the same thing as sigma x and sigma y. So that's what we're doing now. And like before that, we will have tried to go the other way around, which means it's like the sigma alpha and tau alpha, and then you try to back calculate sigma 1 and sigma 3. So now we are at a case that we know about sigma 1 and sigma 3, and since this is sigma 1 and sigma 3, those are on principal stresses, right? So which means on the plane, you don't have sigma yx and sigma xy, so those are the principal stresses. But you induce the stress that you're looking for on any plane inside the solid elements. So you come with an angle alpha right there, and you have the sigma alpha, and also you have the tau alpha. So that's what you try to solve for, sigma alpha and tau alpha in terms of sigma 1 and sigma 3. So you see, if you solve for the equations of circles, you will give this formula. You will give this formula. So pretty much this is like a given. Sigma 1 and sigma 3, and find sigma alpha and tau alpha. And now you have another scenario that you are given sigma x, sigma y, and tau xy, and tau yx. Because now you're no longer on the principal plane, which means you do have a shear stress, which is sigma xy and sigma yx. So you give it that, and then you try to find the sigma alpha and tau alpha. So sigma alpha and tau alpha are the plane within the stress. So this could be sigma y, this could be sigma y, this could be sigma x, this could be sigma x. Oh, sorry, this should be sigma y. And then you have a tau yx and you have tau xy that encounter each other such that the stress elements is in equilibriums. And then you are looking for, one more time, so you're looking for the sigma alpha and also the tau alpha at the given angle. Given angle alpha. Oh, sorry, this need to be this way, angle alpha. And if you solve for the equations, I mean, like if you solve for the Mohr-Circle equations, then you can find the analytical solutions like this one. And you should get the result same as your graphical solutions. And now you do have your shear stress. So those are the analytical solutions, finding the stress within the stress elements from the loading stress on the plane. So principal plane and also like on those non-principal plane. So for example, questions like this, you can solve it for the analytical with the analytical solutions too. So if you have if you plug in the equations, so now this is given the sigma x and pretty much given you the sigma 1 and sigma 3, right? Because it given like a sigma 1 equal 52, you're given sigma 3 equals to 12. So pretty much is on the scenario on the left-hand side on this slide. And if you plug in the equations right there, you try to, well, last time we solved it from a graphical or like a method. And then like we know like this is sigma 1 and this point sigma 3. So we can construct the circles. And now if you so pretty much like from the pole method, we know the stress. And we also know the orientations because the orientation say this is 35 degree. So the loading plane right here is 35 degree. And we want to find out the stresses on this plane. So what we try to this problem is asked for is try to find this like normal stress and also shear stress on the loading on the like plane on the particular plane, not necessarily the failure plane, but like on a plane that within the stress elements at orientations of 35 degree. So we know the orientations. We know the orientations, and actually we know the orientations, and we know the pole. We find the pole, and we solve for the stress. We try to solve for the stress that we try to solve for. So that's this problem, you know the pole, and then you know the orientations, then we can solve for the stress. So that's the graphical method. And we can solve for these problems with the analytical equations too. Just plug in the equations right here. If I do really quick, so the sigma alpha that we're looking for equals to 15.2 plus 12. So there's a sigma 1 plus sigma 3 divided by 2 plus sigma 1 minus sigma 3 divided by 2 times the cosine 2 alpha, which is the 35 degree. So it'll be exactly same as this equations right here. So if I plug in the equations, then I get the answer of 39 kilopascal. So which is this number should be matching this value here, 39. So graphic, if you use like more like if you're more dedicated on the graph paper, then you should really use protractors and also use a compacts to do it. You will have a much accurate results than I do. So and the next part is try to solve for the shear stress. So tau alpha will be equals to sigma 1, which is 52 minus sigma 3, which is 12, and then divided by 2 times the sine 2 alpha. So we exactly the same as this equations right here. So if you solve for that, and then you get an answer of 19 kilopascal. So this your analytical like answer should be same as your graphical solutions. And to be very frank with you, in exam setting, I will not ask you for the analytical approach, because you know, like when you graduate, like you know, when you go work, no one will ask you to punch in the calculator, but very likely ask you, your job will be, if you get paid as engineers, very likely, you know, people need you to do all the presentations, to communicate your ideas with your peers. Could be a geotech, could be a structural, could be another branch of engineers, or the your clients or the public that you need to communicate your idea. Then at that times, like, you know, pretty much you need to present your approach on the Mohr'sCircles. So the problem is, you are given the stress state on the plane, on the elements, on the on a loading plane on elements, and you want to find out the stress that is induced on a plane. So you don't know the directions, but we don't know the directions, but we'll find out later. Even the sigma alpha is not necessarily positive. Remember, we define positive for compressions, and tensions be negative. If we find out the sigma alpha is negative, then the normal stress sigma alpha should be pointing up instead of pointing down. Likewise, clockwise or anti-clockwise for the shear stress depends on our solutions. Okay, so for a problem like this, the very first step we do is we try to set up to construct our Mohr'sCircles based on the given informations. So now we know the stresses on the plane. So we pick one plane. We pick this plane for examples. So we have the stress of normal stress of 12 and shear stress of 10. So if we take this is 12. So let's say this is. So a normal stress of 12 is right here, and a shear stress of 10 is right there. So very important when you do your drawings, make sure the scale in x and y axis they're the same. Sometimes it's tempting to have a y-axis to different than x or the other way around, but make sure they have the same scale. So now I have a scale of a 1 box representing a 5 kilopascal. So I have this point right here. Probably screen. So I have this point right here, which is the 12 and the 10. And my second loading plane is right there, or on this plane. So I have a stresses of 52, normal stress. So this is 20, this is 30. Wait, no, this is right. No, this is 10, 20, 30, 40, and 50. 52 is right there. And I have a negative 10. So this is negative 10. So I have another points right here. So this is 52 and negative 10. So with the two, I can draw more circles. So if you do it properly, you should use a complex to help you. I don't think mine is absolutely accurate, but this is the best I can do. So now we knowing the diameters, right? So pretty much you have 2 points, then you can form the circles because two points allows you to construct the diameters. So now you have we have the Mohr'sCircles, and the next thing is try to find out the pole. Remember the pole method. The pole method is one more times. Is if you know the pole, if you know the stresses, which is the normal stress and the shear stress, and also you know the orientations. So if you know any two, then you can find out the third. So now we need to find a pole. So we look at our loading plane. So we always know the orientations because this is for the blue plane right here now. This is the orientations. It's a horizontal plane, so that's why like it has a degree of zeros. And adding on the plane is this stress. Is the 52 and -10. So this is the plane. So this plane is this plane. So we know we have the orientations and we have the stress, then we can find out the pole. Because the pole, you must meet at the Mohr circles. So that's why this is the the pole. And we can double check ourselves. So the other loading plane that we have, so this is the orientations. We know the orientations of this plane because this is at 90 degree. This is a vertical plane. So this plane is this plane. So again, like it must meet at the pole. So we know we can confirm the pole. So after we identify the pole, we need to work on the to find out the stress, because at the end of the day, we want to find out the stress. And we know the pole now, and also we know the orientations, because the orientations is given. It is this plane right there. It's just this plane. And this plane mean to be at, this plane, let me use another, just trajectory pattern. So this plane mean to be at 55 degree, here 55 degree, just like the one given. 55 degree from the vertical line and 35 degree from horizontal. So I guess like, just like the scale got messed up, when I like do the copy and paste and all, like, I don't directly do on a PowerPoint. So if everything is doing like according to the scale, this should be 35 degree. We are reading 28. This does not mean that it must be 28. I mean to be at 35. I guess just the scale of the diagram, you got like squeezed it. So that's why like the 35 like become 28 here. But it means to be like a 35 degree plane from the horizontal. Okay, so this plane is parallel. So this is supposed to be parallel. So end up like, you have, the orientations and also, the pole. So this two plane is parallel. So the pole, the stress. So the pole, the orientations. So this is 35 degree. And this is the 55 degree. And this is your answer. So your sigma 35 degree will be here is about, so 10, 20, 30, 40, 50, 55, maybe 55, 57. And the shear stress 35 degree plane perhaps maybe about 9 kilopascal. So I just eyeball it. So if you have you do it on a graph paper with better like a drawing tools, then you will get more accurate answer. So any questions on this examples? So the next questions will be the most complicated one that I can give you. So if you can handle these questions, this means they'll be ready on this topic. So now this problem, I give you all, the stress state, the sigma y and sigma x, and also the shear stress of tau xy and tau yx. And very similar. You try to find a loading plane. I mean, like a stress plane within the elements with a 30-degree. And also, you need to find out the orientations. Well, first of all, you try to find the sigma alpha and tau alpha, and also you need to find sigma 1 and sigma 3. And also, we need to determine the orientations of the major and minor principal planes, and also the maximum shear stress and the orientations of the plane. So this is the most complicated, like the most like informative or complicated problem I can give it to you. So let's see whether you guys can solve for this problem. So before I let you to work on it, so there will be a lot of like different plane on this Mohr'sCircle. So after we finish these problems, but again, like the very first step is to identify the stress, all the stress points. So for example, on the red plane you seeing on screen, so we know the stress is -4 and +2. So this is, let me double check. So this is anti-clockwise, right? So this is positive shear stress. And how about the blue? The blue one now we have is, no, hold on, sorry. This is -2, right? Supposed to be -2 because the shear stress here is clockwise. So when we have a clockwise like a moment, a clockwise shear stress, then this is negative. So it should be -4 and -2 right here. So this is our first point. And the other point comes from another loading plane, and this is and sorry, one more thing. This is negative, right? Because this is tensions. This is tensions. This is going the other way. So this is tension. So a negative. And also like it's clockwise. So that's why negative shear stress. So the other one, we have a positive normal stress because it's a compressions. And the moment, the shear stress that you create from the moment that create from the shear stress is anti-clockwise. So it's positive. So we have a +6 and +2 right there. So that's the two points that we have, such that we can form the Mohr'sCircles. Or I hope it looks like a circles. To some degree, more like ellipse. Something like this. So we have our Mohr'sCircles there, and then the next thing is identify the pole. Right, pole method. If we know the pole, we know the stresses, and also we know the orientations. Then 3 of those, we need 2. We can find the third one. So we know the stress, for example, the stress, we know the stress point, and now we also need the orientations. So this is no longer a perfectly vertical plane. It comes with an angle. So you incline us some way. So we need to incorporate the the angle right there. So this plane is parallel to the red plane. So the loading plane on the stress elements is parallel with the plane that we're looking at on the Mohr-circles. So likewise, we also know the plane on the other loading loading plane, the vertical loading plane on the stress elements. And now we can identify the pole. So this is the pole. So we know the pole. So after we know the pole, then we can find the sigma alpha and tau alpha on this plane. So we are looking for the sigma alpha and also the tau alpha. So that pretty much is part A. So part A is we try to find this plane. So now we know the orientations, and then we know the pole. So we have the orientations. Go back to our pole here. So these two lines, they need to be parallel with each other. So this line is this line. And this point right there, there will be your sigma alpha and tau alpha. So any questions on that? So if this is 30 degree, then this needs to be 30 degree. And the next step is asking you the sigma 1 and sigma 3. So where obvious, this point is your sigma 1, and this point is your sigma 3. So this pretty much is like a part B. So you can read from the scale. So this is 1, 2, 3, 4, 5, 6, maybe about 6.2 kilopascal. So you can also read like 6.6. You can also read out the sigma 3, and also you can read out the sigma alpha and tau alpha. And then part C will be asked you find the orientations of the major and minor principal planes. So major principal plane is the sigma 1, and the minor principal plane pretty much is sigma 3. Let me try to use other color. So this is sigma 3 pretty much. So the minor principal plane will be sigma 3. So we are asking for the orientations. Again, if we look back our pole method, if we're asking for our orientations, then we need the pole, we have it. Then also we need the stress, we also have it. So that's why identifying the pole is very important. So now the stress is sigma 1, and the pole, we identified that already. So this will be my sigma 1. This is my sigma 1 plane. So this is my sigma 1 plane. So if we ask for the orientations, so that will be this angle. So you know that this is 70 degree. And here will be 180 minus 17. So this is 163 degree to the horizontal. So that will be the orientations of your sigma 1 plane. Next, you want to find the plane for the sigma 3. So you want to find orientations, you know the stress, and you know the pole. So you know the pole, and also you know the stress at this point. So this will be a sigma 3. Oops. So one more time. So this will be a sigma 3 plane. And yeah, the angle is 72 degrees. So this plane is at 72 degrees. Right there, 72. So that pretty much will finish part C. And part D, last but not least, hopefully I'm not running out of color. So let's use yellow on this one. So we try to find the maximum shear stress. So the maximum shear stress will be this point, the peak point right there. So this is the maximum shear stress, the tau max, maximum shear stress. And we know the stress point, and we know the pole, so we can find out the orientations. So this is the pole, and this is the orientations. And this is your maximum, the tau max plane. And you come with an orientations of 32 degrees. Just try to take a blank sheet of paper and then see whether you can solve this problem yourself. And if you go back to your textbook, there's a lot of like practice problems that you can work on. I think it's like 10.1 to 10.6, the homework problems on page 382 to 383. So go back to your textbook. Go try to practice small problems, and also try to like practice for your homework problems. Really see whether you can solve your homework problem yourself. Because in exam you will have time constraint. So under like 10 or 15 minutes, you need to get like you need to finish a problem like this. So make sure you practice enough to a point that you feel comfortable on solving this type of problems. And we really try to understand the pole method. The next for the next topic, we're going to talk about soil strength. Understanding the there's equations, or there's a formula called the Mohr-Coulomb failure envelope to help us to define shear strength. So the Mohr-Coulomb envelope is this equations. The shear stress at failure, so pretty much this is the soil strength. Is equals to the cohesions of the soil. So the C is the cohesions of soil, and the phi pi is the friction angle of soil, and this like sigma pi v is the vertical effective stress. That we talk about. So pretty much like a Mohr-Coulomb failure envelope telling us the strength of the soils is depends on the cohesions plus the vertical effective stress times the tangent friction angle, which defined this line here. So this is the Mohr-Coulomb failure envelope. So this is the line that like define whether like the soil is fail or not fail, which means like when you have a foundations, whether stable or not stable. And this is when you look at this Mohr-Coulomb failure envelope, it's just in a pond slope form, which means this is remember like the pond slope form. This is y equals m the slope times x plus the intersections. So which means like the x now is the vertical effective stress, the y is the shear stress. And this is our y-intercept, which is the cohesions of soil. And the slope here now is the tangent friction angle. So this is equals to tangent friction angle. So all this term here is we can measure the friction angles and also the cohesions. So after we measure the friction angles in the lab when you take the 368 class. You will spend the time to learn how to measure friction angles, and also to learn how to measure the cohesions of the soil. So if you find out those parameters, then you can set up this like a Mohr-Coulomb Faraday envelope to represent the soil properties that you're working on. And this envelope over here defines two domains. So whatever above it means failure. So when your stress is greater than or touching the line right there, which means like the stress combinations is large enough to fail the soils. And whatever below it, this is stable. And if you realize this is the Mohr-Coulomb space, or the Mohr'sCircle space, right? The shear stress on the y-axis, and the vertical stress on the normal stress. So this is now the normal stress is on the x-axis. So this tells us the stress state at a particular point. So whether you find out sigma 1 and sigma 3, remember this point is just sigma 1, and this point pretty much is a sigma 3. If your sigma 1 and sigma 3 combinations is end up like draw up the Mohr'sCircles that just not touching the Mohr-Coulomb Faraday envelope, that means you're at a stable conditions. Versus if you are sigma 1 and sigma 3 combinations to make your Mohr'sCircles that go large enough to be touching the Mohr'sCircles, then this is failure. So this is essential for a civil engineering project. So for example, if I have foundations right there, so this is the foundations. So before I put on the foundations, so so this is before the constructions. We are looking at soil elements in the ground, right? Just like go back to your lecture number 3, you can calculate your vertical stress, and also you can calculate your horizontal stress. So we have been doing that for homework 3. So the vertical stress is your sigma 1, and the horizontal stress is your sigma 3. So pretty much you on the Mohr'sCircle space, you can identify the sigma 3 and sigma 1. And then like you can set up your Mohr'sCircles. Then in your design, you wonder how much loading for the soil can handle here. Then we can make use of the Mohr-Coulombs and also the Mohr'sCircles. So the combinations of the Mohr-Coulomb. So this is the Mohr-Coulomb envelope with the graphical representations of Mohr'sCircles. It helps us to find out the bearing capacity of the soils. Because at the same site, so this is after your constructions, you put on the foundations, right? At the same elevations, you look at the same piece of soil element now. So you have your sigma H, and also you have your sigma V point, right? But from the foundations, you also have the loading adding on the ground. So you have your new stresses that will be equals to your original one plus your loading, which means in this case now your sigma 1 is increasing, but by how much is the limit? Then you can find out with the Mohr-Coulomb Faraday envelope. So at this point here will be your limit. of the loading that you can find out to back calculate how much bearing capacity these foundations can handle. So this is pretty much just a transition to help us to get you think about the topic of soil strength with the use of Mohr-Coulomb and also the Mohr'sCircles.